Okay, let's now prove some of these facts. Proof. Let's look at number 1 first. So I'm going to suppose that A plus C is equal to B plus C. Okay, so then what do I need to do? I need to get rid of C on both sides to demonstrate that A is equal to B. How can I do that? So if A plus C is equal to B plus C, then by, let's see, by A4, there exists an inverse of A such that inverse of C. So if I add minus C to C, I'm going to get 0. So let's use that. So by A4, there exists minus C in V such that C plus minus C is 0. Okay, so then what am I going to do? I'm going to take both sides of this equation, and to each of them I'm going to add minus C. There is no particular property for that, because simply if I have two numbers that are the same, if I'm adding another number to the same number, I'm going to get the same outcome. All right, so I have that. Then, let's see. So on the next step, what can I do? I can use the associative property, which says that I can reallocate the parentheses. Instead of having A plus C plus minus C, I can redistribute the parentheses to have A plus C plus minus C. And I can do the same thing on the other side. I can write this as B plus C plus minus C. So I'm using the associative law A1 twice to get to this step. All right, so we have that. Now, I know that by A4, C plus minus C is 0. So A4 twice will give me A plus C plus minus C is 0 is equal to B plus, so first time I'm using it here, A4, and the second time using A4 there. So I get A plus 0 is equal to B plus 0. But from that, we have the existence of 0, which is our A3. And A3 says that if I add 0 to any number, I'm going to get that number back. So A plus 0, A3 times 2, I'm going to get A is equal to B. And that is precisely what I wanted to show. Right? So the statement 1 has been proved. Let's look at the statement number 2. What was the statement number 2? 8 times 0 is equal to 0. All right, so how can we proceed here? Let's do it in this way. So I take A times 0, and I know that this is the same thing as, so you see in this case, what am I doing? I'm multiplying A by 0. 0 is something that comes from addition. So I cannot immediately use any addition properties because here I'm doing multiplication. So what's the only property which relates addition and multiplication? That's a distributive law. So somewhere in my proof, I'll have to use DL, distributive law. Okay, but to use distributive law, I have to be able to distribute something. And if I have 8 times 0, there's nothing to distribute here. So I'm going to invent something where I can distribute. So, okay, so I can write this as 8 times 0 plus 0. Why are those going to be the same thing? Because adding 0 to anything will give me that anything. So that is a property A3. Okay, and then now distributive law says that I can distribute. So this is A times 0 plus A times 0. All right, so we have this. And another thing, which is true, is that if I take A times 0, so this was DL, and also if I take A times 0, and to that I will add 0, then of course A3 again says that this should be A times 0. Okay, so this guy must be equal to that, and the same guy must be equal to this. So therefore, we can conclude from this that A times 0 plus 0 is the same thing as A times 0 plus A times 0, right? And one other thing that I can do is by the commutative law, which I think we called A2, I can interchange in my right sum. I can interchange terms so that the sum looks like 0 plus A times 0 is equal to A times 0 plus A times 0. Okay, but now I can compare this to the first property that I just proved. What did the first property that I just proved tell me? It told me that if I have A plus C equal to B plus C, then this is going to imply that A is equal to B. Well, and that's what I have here, right? I have 0 plus C equal to A times 0 plus the same number, right? So then by property 1, it follows that 0 is equal to A times 0, which is precisely what I wanted to show. And let's try number 3. So in number 3, we have to demonstrate what again? So I want to show that minus A times B is equal to minus A B. Well, let's start from 0 times B. Now, 0 times B I just proved by the previous statement, which is 2. And by commutative law, because I proved that A times 0 is 0, but commutative law says that 0 times B also must be equal to 0, commutative law for multiplication, so that's M2. Both of those imply that the outcome must be 0. Fine. But what is 0? 0 is, in particular, can be written as A plus minus A times B. What is A plus minus A equal to 0? That, I believe, was A4. And then distributive law says that this is the same thing as AB plus minus A times B. Okay? Now, but what else do we have? Also, if I add AB to minus AB, that is equal 0, and this is again existence of the additive inverse, which is A4. And so 0 on one hand, so 0 on one hand is equal to this. On the other hand, it is equal to that. So what we got is that AB, so therefore AB plus minus AB, that this is equal to AB plus minus A times B. All right, so we have that. Then by using commutative law twice, commutative law for addition, so that's A2 times 2, I get that minus, in fact, we can try to write this without parentheses now, minus AB plus AB, right? I interchanged two terms in the addition here. That's the same thing as minus A times B plus AB. Well, but again, I can compare this to property I, which says that if I have something plus number is equal to something else plus the same number, then that same number, in this case AB, can be dropped and the equality is still going to be true, which means that minus AB is the same thing as minus A times B. And what is this? That's exactly what we wanted to show. Right, so this statement now is proved. So you see what is a common theme here is that I'm proving very easy and obvious statements here, right? So they seem to be obvious, but I cannot assume them to be true. I can only assume that my axioms are true, and from those axioms, I have to derive the statements of the theory. So that somehow is the difficulty, is suspend your belief that you know that something is obviously true and simply try to see how you can establish that based on things that are known. In fact, one other thing that you can notice here I'm doing, when I proved I, the first statement, I simply used the properties, the axioms. But once I started proving I, the first thing that I did here, not the first thing, but actually the last thing, is that I used the first property that I proved to establish a second property. When I proved the third property, the first thing now that I used was a second property that I already proved. So as you keep going, as you know more and more things, now those things that you already established can be used to prove new things. Okay, let's see what else do we have here. Let's prove property number 4. I'm going to skip. You will do it on your own. And property number 5. So let's suppose that AC is equal to BC and C is not equal 0. This should be very similar to the first property, right? Because you're basically establishing the same statement except that instead of the statement involving addition, you now have a statement which involves multiplication. So that means that your method of proof should be similar. So what did we do in we want to prove the first property? So I'm going to look at c not equal to 0. If c is not equal to 0, then from that, by existence of the inverse of existence of a multiplicative inverse, which is M4, there exists C inverse such that C inverse times C is equal to 1. So then I take my equation, AC equal to BC. And what I can do is I can multiply both sides by C inverse. Again, I can do that because sides are equal, so if I multiply with the same number, this statement must be still true. All right. And then somehow I have to be able to cancel C. So one thing that I should be able to use is I should be able to use the associative law for multiplication, which is the one right here. If I have A times BC, that's the same thing as AB times C. So let's see how we can regroup things here. So for the probably one thing that I would need to do first, I will need to put C next to C inverse in both of these expressions. So then if I use a commutative law, which is M2 twice, commutative law for multiplication, then I'm going to get C inverse times CA. This is the same thing as C inverse times CB, right? So I switched the order of multiplication in both parentheses. So I have that. And then I can use associative law twice. So M1 times 2. And this will imply that I have C inverse times CA. And this is the same thing as C inverse times CB. But then a product of C inverse and C, that is M4 again, is 1. So we get 1 times A is equal to 1 times B. And then the property M3 applied twice again will tell me that A is equal to B because 1 times A is A and 1 times B is B. And that's what I wanted to show. So that property is done. Number 6, the last one in this theorem. So I'm going to assume that A times B is equal to 0, and I have to show that at least one of these numbers, either A or B, must be 0. Well, so let's suppose first that B is not equal to 0, right? If B is not equal to 0, then let me see what would be the most optimal way of showing this. Actually, let's do it this way. So I'm assuming that B is not equal to 0. Then, if I multiply B by 0, I'm still going to get 0, right? No matter what B is. So that would be my property 2, right? Because property 2 said that a dot 0 is equal to 0. So right. So by property 2, b times 0, b times 0 must be equal to 0. And therefore, AB is the same thing as 0 times b, right? Again, in this case, let's make sure that I'm doing things in appropriate order. So b times 0 is 0, but then, of course, 0 times b is also 0, and that comes from m2, right? Because multiplication commutes. So b times 0 is 0 from property 2 that I proved, and b times 0 is the same thing as 0 times b, and both are equal to 0. So then from here, I get that. Well, but then the property that I just proved says that if I have two numbers multiplied by the same non-zero number, then that means that those two numbers must be exactly the same. So that means that from property number 5 that we just proved, it follows that a is equal to 0, right? So that would be the first possibility. Second possibility would be let a not being equal to 0. And I'll ask you to just write it down on your own, but then the same arguments as in 1 will immediately show you that if a is not 0, then b must be 0. So that's a third possibility. And of course, a second possibility. And of course, there is a third possibility. So the only remaining possibility is, let's see, remaining choice is a, b are both equal to 0, because either one is not equal to 0 or both are 0. And so then from this we conclude that always at least one of a, b is 0. And so we proved this statement. Okay, so I hope that you were able to follow this, and in the next part of this lecture, we will look at the property of ordering.